Now that you've been introduced into some of the other functions that we can take a derivative of, we can now apply them using the chain and the product rule. So let's do some fun derivatives. And I think derivatives is all about exposure. It's all about practice. So I just encourage you to do as much practice as possible. And it's actually in some ways a pretty mechanical thing to do, and it's easier than a lot of the math that you've learned before. It just maybe initially looks a little abstract. So let's say that f of x is equal to, let's say, the sine of 3x to the fifth plus 2x. So what is f prime of x? What is the derivative of this function? Well, we use the chain rule again. We take the derivative of the inside. So what's the derivative of the inside? Well, that's just 5 times 3 is 15 x to the fourth, right? Plus 2. And then we take the derivative of the larger function. In the last presentation, we learned the derivative of sine is what? It's right, it's the cosine. So it's times the cosine of this expression right here. 3x to the fifth plus 2x. Pretty painless, no? Let's mix it up even more. Let's say that, let me switch colors just to not be monotonous. Let me pick powder blue. Very nice. Let's say that y, and I'm going to switch notation on purpose so that you get used to the various notations you can use. Let's say that y is equal to, let me think of something good. E to the x times cosine to the fifth of x. That looks daunting to me. Let's see if we can break it down using the product and the chain rules. So let's see. We want to figure out dy dx. We want to figure out the rate at which y changes relative to x, or the derivative. Apply the derivative to both sides. Well, let's use the product rule. Well, we're going to have to use the chain and the product rules. So first, we take the derivative of this first term. And once again, we learned in the last presentation the most amazing fact, one of the most amazing facts in the universe, that the derivative of e to the x is what? It is e to the x. That blows my mind. E to the x. Once again, I've taken the derivative, and it's the same expression. Amazing. And then I multiply it times the second expression, cosine to the fifth of x. And now, to that I add the derivative of the second expression. Now this will be a little bit more interesting. So this is cosine of x to the fifth, right? This is just another way. This is just another way of writing cosine of x to the fifth power, right? And I think that'll make it a little bit more clear. This cosine superscript 5, this is really just cosine of the fifth x, just means cosine of x to the fifth. So now the derivative is a little bit clearer. We can use the chain rule, and once again, we're just working on this right half. We take the derivative of the inside. What's the derivative of cosine of x? Yep, you're right. Well, I don't know. I didn't hear you, so I don't know. I'll assume you're right. The derivative of cosine of x is minus sine of x. And that's something you should memorize, although you should prove it to yourself as well. So we take the derivative of the inside, minus sine. Derivative of cosine of x is minus sine of x. And then we take the derivative of the outside. We're just doing the chain rule. So it's 5 cosine to the fourth of x. So there, we took the derivative of this piece, and then we have to multiply it times this first piece. So that times e to the x. Interesting. You could simplify this if you want, but you get the point. I mean, simplifying it from this point is really just kind of algebra, and I think you get the idea. Actually, everything we're doing is algebra, but we just use the, if you realize it looks like something fairly complicated, but we just use the chain and the product rules. Let's do some more. I will now switch to magenta. Let's say we want to take the derivative dy dx of, let's see, some big expression. Let me do something creative. Let's say the natural log of x over 3x plus 10. Whoops, that's supposed to be a curve. That's supposed to be parentheses. So the natural log of x over 3x plus 10. So you could use the quotient rule if you took the time to memorize it, which I've never taught you because it's really just the product rule. So I like to just rewrite this as the product rule. So this is the same thing, this expression. Once again, we're taking the derivative, so I'm not going to keep rewriting this. But this is the same thing as taking the derivative of the natural log of x times 3x plus 10 to the negative 1 power, right? 3x plus 10 in the denominator is the same thing as 1 over 3x plus 10, which is the same thing as 3x plus 10 to the negative 1 power. Now we can use the combination of the product and the chain rules, and we can solve this sucker. So let's do it. So the derivative is, we take the derivative of this first term, the natural log of x, and we learned in the last presentation the derivative of the natural log of x is 1 over x, which is pretty cool in of itself. And we multiply that times the second term, so times 3x plus 10 to the negative 1 power. And to that, we add the derivative of the second term, and we're going to multiply that times the first term. So the derivative of the second term, so first we're going to have to use the chain rule. We take the derivative of the inside. Well, the derivative of the inside is easy. The derivative of 3x plus 10, that's just 3. 3. And then we take the derivative of the whole thing, so it's negative 1. That's 3 times negative 1 times that whole expression to the minus 2. 3x plus 10. And of course, this whole thing times the natural log of x. We could simplify that. Let's see, this is 1 over x and 3x plus 10 to the negative 1, so we could rewrite this as 1 over x, 3x plus 10. And let's see, plus 3 times minus 1, so we could say that's the same thing as minus 3 ln of x over 3x plus 10 squared. I think you see how I got from here to here. I just manipulated the exponents and multiplied some numbers, etc., etc. Let's just do one more, just to hit the point home. You really have the tools now at your disposal to do a lot of derivative problems. Probably, actually, most of the derivative problems you'll face in the first half year of calculus. So let's say I'm going to switch to green. So I want to, let's say y. I'm tired of y. Let's say that, I don't know, p is equal to I don't know, sine of x over cosine of x. Let's figure out what dp to dx, right? The rate at which p changes to x is. So once again, this is the same thing as sine of x times cosine of x to the negative 1, right? So we can just do the product and chain rules. So the derivative of the first term, derivative of sine of x is cosine of x times the second term times cosine of x to the minus 1. And then to that we add the derivative of the second term. Well, we have to use the chain rule here. So we take the derivative of the inside. Well, derivative of cosine x is minus sine of x. And then times the derivative of the outside. Well, that's minus 1 cosine of x to the minus 2. And then we multiply that times the first term, sine of x. So let's simplify that. So this is cosine of x divided by cosine of x, right? You see how this cancels out? This is cosine of x over cosine of x. So this is equal to 1, right? Cosine of x divided by cosine of x is 1. And then this minus sign cancels out with this minus sign. And this sign, and this, we have sine times sine over cosine squared, right? So this is equal to 1. I'm going kind of fast because I'm about to run out of time, but I think you get what I'm doing. So this is sine squared x over cosine squared x, which is actually equal to, right? What's sine over cosine? 1 plus tan squared x. And if you know your trig identities, that equals 1 over cosine squared of x. And of course, what we just proved is that the derivative of the tangent of x is equal to the secant squared of x. I hope I thoroughly confused you in that last problem. I'll see you in the next presentation.